Hi, this is a quick demo to show you how the Pontus Vision Thread Manager GUI works. So first you log in. Default username and password is root, PA55WORD. And as soon as you log in, the first screen that you get is this time series graph. Right now it's empty, so we need to select a host. This gives you a breakdown of all the different machines that you have being monitored. And then what we can do is just select a specific time period for that. In this particular case, it's been a while since we've done any tests in there, and you can basically zoom in and get finer and finer granularity in the environment. So as you zoom in, you get a time series of previous scores on the system. And as soon as you click in one of these little score points, what we'll do is show you at that point in time what the environment was doing. So we can see in here there's a red flag stating that there was something abnormal with the environment, and we'll see what that was in a second. So we can basically see the solution for the system showing you which threads for the application. So the applications are on the columns here. We have interrupts in this case as well, and then we have a list of all the different cores that we have. Now you can see in here this was actually a passive mode experiment, so we weren't pinning the CPUs, and you can see we ended up with -1% CPU utilization on some of the cores here. So that's basically why the system was complaining. Because we're not pinning threads, the scheduler can move them around, and sometimes we overcount the CPU utilization. So it's a telltale sign that there are definitely optimizations to be made. We can also have in the different tabs in here a view of the actual hardware or the different software components so happen there. So what we can see in here is there is basically an interrupt, an IRQ in here. This is IRQ 114, and we put a negative process ID number in there just to indicate it's an interrupt. We can see another one in here, so that was a different NIC on the same machine, IRQ 115. And then in this whole row of little blue squares here, we see in this particular case it was a multi-threaded application called ADS that was communicating with the network cards in one side, with the network card on the other side as well, and we can see a lot of information about what type of connection that was. So this was a socket connection. These were the port numbers. The number in here has how many bytes were being sent. You can see which threads within the application were actually sending and receiving the data. And again, this allows you to basically search for that information and then zoom into the specific components quite rapidly. So a few of the other features you can have in here is you can actually have this Cosmos view, so you end up with a cluster. We're using physics to render all these different components in here, so you can see what's talking to what in a different way. It's a bit of a spider web. You can click on a component and see. You can also have the same information in this app links tab. So this allows you to search through all that plethora of different connections between the threads, and then sort it out really. You can filter it by just the internet connections or the iNet, so you can see all the different lines that you had in here in a tabular format. Back on the solution again, if you double click on a core, you can basically see the layout of the machine in here. The green cores are basically closest to the core that you had in terms of memory access, and then the red ones are further away. So in this case we have a 2-socket machine. You can see physical CPU 1 here, the green cores and the blue one are basically on physical CPU 0. And what we can also do is run a simulation, or basically within the realms of the simulator itself try to find a better layout for the threads. Once you finish running a simulation, then what the system will give you is basically a different layout of the threads. You can see we no longer have any overcommitted cores in here, and what we'll be doing, what the simulator does, is it uses that information that we saw in the software tab in here, that spider web of connections, to basically pin the threads, taking in consideration the hardware information that we've provided via the agents again, and again just approximating the threads to the interrupts as much as possible. So if you have threads writing information, they will basically be close to the NICs, at least in the same NUMA zone or in the same physical CPU as much as possible. And the model will also tend to just remove some of the unnecessary threads away from the green zone where your I/O traffic is happening. For instance, you can see some of the threads in this example here have relatively few connections. They're weak connections, some and have relatively little CPU utilization as well. So it basically allows you to be quite selective on what goes where, much more so than if you're doing the stuff by hand. And again, especially without having the luxury of having the source code for the application. Now, one of the interesting things that we can do with this is, again, in addition to being able to color code the cores based on NUMA zones, is to also do what-if analysis. So if, for instance, you have different types of hardware available and you want to go over a hardware refresh cycle, then you can actually take pre-profiled instances of hardware, replace them. So in this case, I've just replaced the original server with a much larger box here with the new machine. You can score already is miles better than even the optimized score that we had before. So what I'll do is I'll pause the simulation now, and you can see straight away that this is actually a much larger machine. So we have 64 cores in this one in particular. This is actually 32 cores hyper-threaded. So we can see, if I highlight core 0 here and I scroll down, core 32 is highlighted in lighter green. So that's the hyper-thread for that previous one. You can also see a feature that we have in here that allows the agent to set up junk cores where none of the applications that we care about should be running, and those are reserved for non-essential tasks from the operating system, including the agent itself. So again, this makes it for quite a powerful environment. We can also manually drag and drop components in here, and this allows you to do some manual planning, playing around with the score. So for instance, if we move this writer thread in here that actually connects to the IRQs to a different NUMA zone, so we're going now from CPU 0 to CPU 1, you can see that the solution has actually worsened quite dramatically. So we went from a lower score of 2866 to a much higher one of 3310. And so again, if I drag and drop this back where it was, you can see that it returns back to normal. And then the system will also not allow you to have an interrupt in the wrong location. So if I try to drag and drop an IRQ to a wrong area, so it basically will find it will raise a red flag in the environment again. And again, if you either drag it back or you rerun the simulation again, it will just move the threads back to the location that they were. Or again, it can try to find even a better solution than what we have in here. And again, this information is available historically. You can click on any of these different graphs. We can also show stats like total CPU utilization, when you're running the agent in an active mode. You can also see when the thread pinning strategies were requested and when they were applied as well. This concludes the quick tour of the Thread Manager GUI. Thank you very much.